Hi YouTube. I want to talk about the problem with Mach's principle and I call it the background relevance problem. So, like in my model, the symmetry of angular momentum. So, say you have a rotating ice skater, and you distribute the ice skater's angular momentum to the entire universe. Well, if you were to do that, the rotation would be absolute. It would have no effect on the background universe because the universe's mass, the universe's moment of inertia, is infinitely greater than that of the ice skater. So the proposal that I have is that it doesn't like operate that way. Like we have to have a better understanding of the inertial frame, the inertial field, and whether it has a property I call independence. So whether the inertial frame has the property of independence, and I think it does. I believe it does. And to explain to you what the property of independence is, I just asked the question. To what extent do subsets of the universe behave as universes unto themselves? And the inertial field has this property. The effect it has is kind of like shimmy on a steering wheel. This is very pertinent to rotation curve discrepancies and how they work. So I was explaining in Mach's principle, the democracy of matter, how the galaxy was rotating and it was voting to itself, we are fixed, we are fixed, we are fixed. But that is going on, but the fixed rotational frame is actually lagging behind the star's actual velocity. And the reason it does that is because the background frame drags it back. But if like the inertial frame was like rigid, like there was no independence principle, then rotations would be completely absolute and there would be no rotation curve discrepancy. But because of this property of independence, we see a rotation curve discrepancy, and that is why there is a phenomenon like a rotation curve discrepancy in terms of Mach's principle. So the basic idea is that local frames have more influence than the background one. So subsets of the universe behave independently than independently from the whole, basically, to some extent. They're somewhere along on that spectrum, and that's basically what I want to explain. Just to resolve this background relevance problem. So, since I'm on the topic of the problems with Mach's principle that I'm addressing, the second one is I call it the disagreement problem, where I want you to think of Mach's principle in a different way. So, instead of having one object and then the background frame being there's a background frame and then there's a single rotating object. What I want you to imagine is there is a background star, and in the foreground are multiple rotating objects separated by some distance. And so how do you resolve the background frame's rotation? And say you have two rotating bodies side by side, and one's rotating in one direction, the other's rotating in the opposite direction. The way I want you to think about these are the rotating frames emanating from both these objects. Imagine it so one relative to one rotating frame, the background star is going in one direction, and relative to the other frame, the background star is going in the opposite direction. The way I want you to think about it is these rotational frames are superimposed upon one another, and so the resultant velocity, I would say, or the resultant rotation of the two don't cancel out. they're like additive. And so that's where I'm trying to say that the background frame is undefined. You can't really define it in terms of any single rotation around all those objects. You really have to look at it from the perspective of every perspective in the foreground. And it doesn't make sense if you try to resolve it in a particular direction, because the disagreeing frames of reference, they kind of have this additive effect on the centrifugal acceleration of the background star. And so like resolving the background's rotation in a particular direction is flawed. It's not a true indication of what rotation the background star or the background stars are rotating. So that resolves that problem. All right. Have a good one, YouTube. Bye.